Okay, this is my physics lab 3, and we're going to be looking at the mass of a black hole. Important concepts in this lab that we cover are gravitational force in orbit, a non-constant force in orbital motion, how the change of momentum corresponds to force, um, parsing Fnet into parallel and perpendicular forces, and observing the surroundings to estimate attributes about the system. So in this case, we observe the orbit of the star to estimate the mass of the black hole. Important formulas are the momentum principle, F net equals dp over dt, formulas for parallel and perpendicular forces, and the gravitational force, which is equal to gravitational constant times the mass of the black hole times m star divided by r squared times r hat. So for our experiment model code, I changed two initial conditions. I obviously set the seed to my email, and then I changed the star.m variable, which is the mass of the star. I set that equal to 2 times 10 to the 30th, which is what was given in the problem. And delta t, I set that equal to 86,400 because that is how many seconds are in a day. So for our calculation loop, I plugged in the momentum formula, P equals mv, for the initial and final momentum. I plugged in the change of velocity and momentum formulas for delta P and delta V. And then for dp/dt, I did the change in momentum over change in time, and then Fnet equals dp/dt. We know this from the momentum principle. So, more changes to the calculation loop. Some important ones to point out are dp dt parallel, which in this case I did the change in the magnitude of the momentum times p hat, and we can get that from the formula for a parallel force. And I set that change in parallel momentum equal over change in time equal to F net and F net parallel. And then for our perpendicular force, I found the change in perpendicular momentum by subtracting the change in parallel momentum from the change in total momentum. And then I set F net perpendicular equal to the change in perpendicular momentum. So for my experiment, we added some arrows to our code to represent the forces. And as you can see in the video here, the orange arrow represents F net, and that points towards the black hole at all times. And the magenta arrow points parallel to the motion of the star at all times. And the cyan arrow points perpendicular to the motion at all times because that is F perpendicular. We multiplied all of these arrows by a very small arrow scale because the forces are very large. So calculating the black hole, the mass, I did this by rearranging the formula for gravitational force so that the mass of the black hole was equal to r squared times F, the force of gravity, which in our case is F net, and divide that by the gravitational constant times the mass of the star. So what I found the mass of the black hole to be 1.6 times 10 to the 34th. I did this by taking the average of the black hole mass at all of the points from the calculation loop. So comparing F net and the change in momentum over change in time, as we know, the momentum principle says F net equals dp dt, and this also applies for F parallel and F perpendicular. So F perpendicular is equal to the change in perpendicular momentum over change in time, and F parallel is equal to the change in parallel momentum divided by the change in time. So what if we had a different black hole mass? Essentially, you cannot have a different black hole mass and the same trajectory in this experiment. This is because the only force acting on the star is gravity, and the gravitational force depends on the mass of the black hole. So if you change the mass of the black hole, the gravitational force will also change, and if the gravitational force changes, the trajectory will also change. Thank you for watching.